Alright, so far we saw that text-to-mesh can take texture from an object that you mention in the prompt. In our case, we use the word cactus, and it took the texture from cactus and transferred the texture as style into a 3D object, which in our case is a couch. And it tried to keep the topology and geometry of the couch intact, which is really cool. But a couch has a very simple topology. What if we give text-to-mesh a very difficult topology? One of the very important aspects of text-to-mesh is global and local textures. And text-to-mesh is really good in capturing both the global textures and the local textures. And in the paper, they mentioned that a global texture is the combined architecture, or I should say the geometry of the object, and local textures are the local features. For example, in case of a human, the head, the legs, the hands, how they should look like. These are local features. And it would be really cool to experiment with an object file of a human being to see how that performs. So let's do it. In figure 3 of the paper, we see that there is a really cool example of how text-to-mesh is able to capture the local features of a 3D mesh. And you can see that the example shows that it can transfer styles from different characters into a human mesh. So it says, given the same input bare mesh, our neural style field network, which is, by the way, the name of the neural network that this paper came up with, produces deformations for outerwear of various types, capturing the fine details such as the creases in clothing and complementary accessories, the distinct features such as muscle and hair, which is really cool. And the synthesized color consider both local geometric details and global part-aware semantics. For this, by the word semantics, it means that a Hulk should be green and it should have hair that looks like a Hulk, as in it cannot have a mask like Batman. So these are the semantics that comes from the clip model, because it captures the semantic meaning of text and their corresponding images into same embedding space. And that is something we can use to experiment with as well. And to do that, we go straight into demo, and there is a shell script called run_ninja. If you look inside it, it says to look for a mesh file called person.obj. So let's do that. If you go inside data, source meshes, you will be able to find person.obj. And of course, we don't have a MTL file for it, because we don't need an MTL file to run text-to-mesh. So what we can do is we can copy the whole thing from here, and let's run it, but change some things here. For example, let's try a different seed, because we don't want to generate something similar that is given in the paper. And let's try some new kind of text prompt. So instead of ninja, let's try astronaut. So let's say a 3D rendering of an astronaut in Unreal Engine. And let's not mess with any other arguments because we haven't talked in details about them, and let's try to run it and see what it comes up with. Fantastic. We finished running our model. Now let's look at the results. To get the results, we go into the results directory, the demo, people, and Astro. And remember the prompt that we used. It's a 3D rendering of an astronaut in Unreal Engine. So let's look at the final cluster. That's not bad actually. It does look like an astronaut. The face could have been better, but that's just parameter tuning here and there that we can use to play around with. Let's look at the iterations that we got. One thing that you can see is that the first image is the front view of the human mesh, and you might have noticed that front view is also one of the parameters in our while running the main.py function, and in the upcoming videos we will talk about the effect of front view on the results. So let's look at the results after the first iteration, first 100, second, first 2000, and it looks like it tries to improve on different local features when it reached sort of the later iterations of the while running the algorithm, which is exactly what we wanted to see. Now we should be able to look at the output obj file on Blender. So let's do that. General, remove the cube, import obj, desktop, results, demo, people, astro, final obj. So that is our results, and you can see that the textures sort of changed to make the model look like an astronaut, which is pretty interesting. And again, when you click on the texture, you don't see any textures. So once again, we have to run the texture.py. So let's do that. So let's clear all this stuff from here, and let's run texture.py, and we have kept everything inside the people folder. So people, astro, I think it's called person_final. So I'm gonna call it person_final text, and copy this portion here, and we're gonna call it person_final, and we don't need this part, so that should be it. Perfect. Let's give it a second, and once it's done, we can look inside, and here is our texture file in PNG format, and we have a person_final_text, which is what we expected. And now we can import that into Blender using import orefront obj person_final_text, and let's move it to the side to see the difference. There we go. Perfect. Again, the resolution is not as good as we hoped for, but not too bad actually. So that concludes the first portion of this video series, and in the next video we will go over even in more depth of the algorithm. We will discuss paper within 5 minutes, and then we will talk about a little bit about the parameters. So if you like this video, don't forget to like and subscribe to my channel, and I'll see you on the next one. Have a good one. Bye bye.